don't know what they're going to do, you ask, okay, well, I'm going to get a bachelor's of arts or I'm going to get a bachelor's of science in psychology. I was like, well, that's great. What are you going to do with it? I don't know. Why don't you get a degree?
Well, everyone has to find their way, man, you know. The moral of my story was that sometimes it's about who you know and getting lucky. So letters of recommendation, all that stuff, I'm more than happy to fill out because you never know when one little letter could make the difference.
Well, I do know that because back when I was young and dumb, well,
You're implying that those days are over?
The days where you say shoulda, woulda, coulda, yeah.
Okay.
You know, I'm trying to avoid those. I've limited them so far in my older age, I guess. But when I was younger and dumber, I turned down an engineering internship at Southwest Military Research Center.
Oh.
And they only offered 3 interns per year. And it's a paid internship to work study where you work with them for a semester, and then the next semester they pay for you to go to any college that you want to go until you graduate. And then at the end of the internship, if they like you, they'll hire you, which 99% of the time they do because they've stuck you around and paid for your school. And
well,
I declined the offer.
We learn, right? Lessons learned.
Like I told my wife, I said, look, if I would have taken that internship, I was like, we'd be having this conversation with my Mercedes-Benz sitting outside. That's not happening.
All right, well, lessons learned.
It's time.
Let's get going with 6.2. Any questions on homework?
So far, no.
We're okay? 6.1?
I didn't get all of it, though, but so
Okay.
far what I've been working on.
Yeah, the homework was pretty much in line with what I did in class. So if you did it, then you shouldn't have run into too many things. Today, we continue with the same concept, 6.2, and we talk about one-to-one functions. Now, you might see me write 1-1 instead of writing the words one-to-one. Okay, one-to-one functions. So there's some definitions, that are going to get us going here, but I don't want to get, bogged down with definitions. I want us to think through it first, try to visualize what's happening, and then from there, I'll try and define things. We talked last time about if you have a function that you can compose it with another function, f of g, or you can do g of f, or all these different variations, right? And I said sometimes it works out that one function will undo the other. And when that happens, I said that we were going to call it an inverse, right? Something like that. In order for it to happen, though, the function you start with, the f, has to be a one-to-one function. So let's discuss that, one-to-one. So here's a picture. Domain, range, here's a function f. So I'm going to draw a picture of what's happening here. Let's say this function, you take the numbers 1, 2, and 3. 1 gets sent over to 3, let's say 2 gets sent over to 4, and let's say 3 gets sent over to 7. This is a function, because to be a function you have to have, for every input there has to be one output. So 1 goes to one place, 2 goes to one place, 3 goes to one place. But it's also a one-to-one function because each of these not only go to one place, on this side these only get touched, or they only come from one number. So I'm going to compare that right there to something else which would not be one-to-one. So here's 1, 2, and 3. Let's say we had 3, 4, and 7. Let's say 1 went to 3, 2 went to 4, and 3 went to 3. Would this still be a function? Yes. No. Yes, it would. Because to be a function, each input just has to go to one place. So does 1 go to one place? Yeah. Does 2 go to one place? Does 3 go to one place? Yes. So this is a function. I'll call this g. This is a function, yes. Is it one-to-one? No. Because 3 gets hit twice. A function? It's a function, yeah. So one-to-one is a special type of function. Functions that are one-to-one have special characteristics. This one is one-to-one. Every input corresponds to exactly one output. Here, every input does not correspond to exactly one output. Here, there's an output that comes from two inputs. Make sense? And you can never have this happen, right? You can never have one go to two places. Then that wouldn't even be a function. Now, why is it that you think we need functions to be one-to-one in order to undo them? Because that's what we were talking about last class. Like, you have a function, and then you come in with another one that undoes it. Why do you think we need this case in order to ever undo something? Think about that one and what would be wrong. What would be hard to determine?
Because then if you work backwards, 3 would have 2.
That's right. If I tell you, hey, look, over here, I'm at 3, where are you going to send 3 back? To 1. Here, 4, you're going to send it back to where? 2. Here, 7 is going to go back to 3. Over here, though, if I say, hey, where does 3 go? You got to send it to 2 different places, and then this direction, it's not a function. See how 3 splits off? So a one-to-one function is one that is going to allow you to reverse it. So one input to one output, it's unique. It's a unique output. Now let me read you what the book says. A function is one-to-one if any two different inputs in the domain correspond to 2 different outputs in the range. Right? So any different 2 here correspond to 2 different ones here. All right? That's what it says. I'm not going to write that down because it's in the book. All right, so let me see if I can show you visually some examples, and if you can tell me whether or not these are functions and whether or not they're one-to-one. So, example, are these functions are they, if so, are they one-to-one? Okay, example A. Let's take a function that we've worked with in the past, a line. Is a line is it a function, and is it one-to-one?
Yeah, it's a function, yes.
How do you know it's a function?
Because it doesn't go...
Vertical line test.
Yeah, vertical line.
You remember the vertical line test? That's what we used to check whether or not something was a function. We drew vertical lines. We could only hit it one time, right, at the most? So it does pass the vertical line test. How do we know it's one-to-one?
Because for every x, there's only one y.
So for every x,
Or for every y, there's only one x.
for every x, I go to only one place, right? And if I were to pick any y value here, right, so let me just pick a y value right there, it's going to go back to only one place. So maybe it'll be easier for me to say yes to both if I show you an example right next to this of something that fails to be one-to-one. So is this a function? Yes, passes the vertical line test. Is it one-to-one? No. So
You can take a point on there and check it has 2.
yeah, let's say we take this point. Let's just say that that's 3. That actually comes out here and here, right? There are 2 points on this graph that have a y coordinate of 3. And that means they come from 2 different inputs. Well, sorry. They come from 2 different inputs. Do y'all see that? So 2 numbers, 2 x values go to the same y value. So maybe there's an easy way to check visually. I mean, there was an easy way to check if it's a function. We did the vertical line test.
Could you just hit a horizontal line?
Yeah, why don't we just turn our line sideways, and wouldn't that test to see if we have more than one y value? See, if I hit both of these, right? That means I have 2 y values that come from 2 different x values. And so that's what we have. It's called the horizontal line test. It's a test to check if you're one-to-one. So again, I'm not going to write down the horizontal line test because it's in your book. If every horizontal line intersects the graph of the function at most one time, then it's 1 to 1. So you can just never hit it more than once. Here I do, it fails to be 1 to 1. So the answer here, function yes, 1 to 1 yes, this one function yes, this one 1 to 1 no. Got it?
But like if you were to flip the second one, if you were to turn that like 90 degrees to either side, it cease to be a function, but it wouldn't be 1 to 1.
That was what I was going to ask you next.
Okay, sorry.
No, it's good. How about this one?
No longer a function.
It's not a function, but it will pass the
Function 1 to 1.
function no 1 to 1. Yes.
Function no because it fails vertical line test, right?
That's correct.
Hits twice, it's not a function. 1 to 1. What? Come on, be confident. It's not a function and you can't even talk about 1 to 1. Good. Read this. Are these functions? If so, are they 1 to 1? See, you can only talk about 1 to 1 functions. If it's not a function, then you can't talk about 1 to 1 at all. So
Like square root would work.
square root.
Like I think you're talking about like maybe the square root of x.
You're talking about specific functions. Yeah, square root of x would be a 1 to 1 function. Yes. So here I'm going to put NA. Have you all seen that? Like not applicable, like does not apply. In 1 to 1 doesn't apply to something that's not a function. All right. Very straightforward, right? There's no hidden stuff here. Okay. That's the easy part of today. All right. If f is a 1 to 1 function, so if you're looking at, if you have a function, someone gives you a function that is 1 to 1, so it passes both the vertical and the horizontal line test, then there must exist a function which we write f with a little negative 1. Okay? Which is called its inverse. So if you have a 1 to 1 function, there must be a function that basically undoes your f, and it's called f inverse. Inverse. Further, hold on. If we take f and we compose it with its own inverse, because that's what we did last class, right? If we compose it with its own inverse and we plug x into it, what should it spit out? The same. So think about this. The way this works is that x goes, in this order, it would go x goes into the inverse first, right? Then that goes into f. What should come out? So x goes in, goes through, gets, what comes out?
Should be the same.
Just should be x.
It just should be x, exactly.
Because the f and then the f minus 1 cancel out.
Cancel each other out and leave the x unchanged. Yes.
Does f inverse have to, like, does the inverse of f have to still be a function?
Yes.
So,
Like in the case of the
And it has to be 1 to 1.
okay.
in the case of like say a linear one, it's just y equals x, then its inverse would be y equals negative x.
Nope. It would just, yeah, no, be careful. It's not, this negative 1 doesn't have anything to do with, like, it doesn't change the sign. This is notation. This is just the way I let you know it's the inverse function. The natural question would be, if I give you a 1 to 1 function, can you give me its inverse, right?
Yeah.
That just hang tight. That's where we're going. I got to show you what the properties are first.
I was about to ask if there's any scenario where that won't work.
We'll have to pay attention to domains when we do it, but okay, so if you have f and it's one-to-one. It must have an inverse function. Here's one property. But the composition, I'm put and, the composition must work both ways. Do you remember last class I did show you some examples where we did f of g of x, we got an answer, then we did g of f of x backwards the other way, and we didn't get the same answer? Right? They were different depending on the direction. Well, if you're working with a function and its inverse, then they must both spit x out. So they must change each other back to what they were originally in both directions.
Kind of like y equals x, it would still be the same.
Yeah, y equals x turns out to be its own inverse. But, all right, got it? This is an important note. So let's check. I'm going to give you a function, and I want us to check that this other function is an inverse. Example. Let f of x be equal to x plus 1 over 3, and g of x be equal to 3x minus 1. Are these inverses? No? How do we check to see if two functions are inverses? What must happen?
If you do g of f of x or f of, or yeah, if you do g of f of x, it
Mhm.
should equal x.
And if we do
And if you do
f of g of x, we should get. So we need to do the f of g of x and the g of f of x both, and we need to get x both times. So I must check.
so you have to do both.
You have to do both. Check, first of all, f of g of x must equal x. So we did this last class, right? This means, this is a question, right? Is this true? So let's find f of g of x. F of g of x means f with g plugged in, which means f with g is 3x minus 1. If you plug that into f, that means I'm replacing that x right there with 3x minus 1. So what would you get there? 3x minus 1
3x over 3.
plus 1 over 3, right?
And then you combine the 1 and the minus 1.
These would go away. You get 3x over 3, which is x. Check. So it does work that way, right? 3x over 3 is x. Then, hey, yeah. We check the other way? Okay. You must check now g of f of x equals x. Question, is that true? So let's go ahead and write that one. That means we take g, inside of it we plug in f of x. That means g with x plus 1 over 3 plugged in.
And then 3 times x plus 1 over 3 minus 1.
3 times x plus 1 over 3 minus 1. Yeah, that's what it is, right? Plugging in for this x, that expression right there.
So then the 3 in the variable and then the 3 that we multiply by would cancel each other out?
Yes, these will cancel. Very good. These 3's can cancel. Or you could distribute it through and then split it into 2. Either way, this is like 3 over 1. So this 3 and this 3 are gone. And then you're left with x plus 1 minus 1, which is x. Check. So are they inverses? Yes. That's what you have to do if you are ever asked on a test to determine whether or not two functions are inverses. You don't just like plug in a number and see if it gets switched back and forth. You have to show these two things are true. Any questions on that? All right, I'm going to give you one to work. All right? Let's see if you can do this one. I'm going to give you two functions, and I want you to verify that they're inverses. Or, see if they are. I'm not going to tell you whether or not they are. Yep, they could or they could not be. You want easy, hard, medium? What do you want? Medium. Okay, we'll start with somewhat easy. X cubed minus 1. G of x is cube root of x plus 1. Okay, that's kind of a warm-up problem, all right? After you do that one, try this one. Everyone understand what you're supposed to do? Verify that those are inverses. Or check to see if they are. If you need a hand, just raise your hand if you have any questions. Yes, you're going to have to find an LCD on the bottom, which would be what? 3x minus 2. Now, there's other ways to do this without doing LCD, but, well, you could multiply this by the common denominator, top and bottom, but I like the idea of doing LCD. I'm just trying to say there is more than one way.
I mean, since you're doing LCD, couldn't you just look at it like 3x over, or 3x minus 2 would be what you'd have on top if you had a 1 and just put that negative on top? Like, so do minus 3x plus 2 on the top? Like, just for the bottom portion, just to get rid of that 1.
Since it's a 1, what he's saying is infinity.
Up here?
Yeah, like to, like just look at that as minus whatever the denominator is.
Yes.
The numerator.
Yes.
Does that make sense?
Yes, I understand what you're saying.
Yeah, like that.
Yes. That's what I'm going to do. I'm going to rewrite it like that. And then I can put these two together, can't I? And we have to be real careful there with that minus sign, right? Because that minus sign's got to go through to both terms, doesn't it? So this minus right here, critical that it goes through both of those. So it's 3x, take away 3x, add 2, all over 3x minus 2. I'll flip it in just a second. Let me just clean up that. This right here is just 2. Questions? Well, yeah? Okay. And now when we have division, we can reciprocal flip. So we get 2x over 3x minus 2 times 3x minus 2 over 2. The 3x minus 2's go away. 2x over 2 is just x. Check. Are they inverses?
That wasn't a lot of work.
That's half of the work.
Well, that's half the part. We gotta-
That's half the work. Now you have to show it the other way.
And you said you could flip it before putting in the -1, or it's just not ideal to do it?
You can flip it. What do you mean? Like,
How you just did it right now?
can't do that with the -1 here. Mm-mm. Nope. Yeah, trying to think of a way I could convince you of that easily. It's hard to think of something where I could convince you. Let's just say this is kind of the same format. You've got a fraction over a fraction minus 1. If you flip it, how would you try and flip this? You know what I'm saying?
Yeah.
Would you go like 2 over 4? Then what are you going to do with this?
Doesn't stay down there.
Oh, yeah, no. Because look, if that stays down there, but first of all, let's just look at what this answer is. Okay? This is 2/3 over. 4 over 2 is 2. 2 minus 1 is 1. 2/3 divided by 1. The answer to this should be 2/3, right? But if you flip that 2/3, 2/4 over what, -1s or something like that? I don't know what you would still do with that.
It's because it's a method, right? The flipping is actually a solving method, right?
The flipping is just rewriting division. The problem is that here, this is not a fraction, a single fraction yet, because it's 2 terms. You have to put it into a single fraction before you can flip it up. Okay? Good. Yes?
Okay, so what I was going to ask, like whenever you're adding or subtracting to a fraction,
Uh-huh.
just essentially take whatever the number you're adding or subtracting by,
Uh-huh.
and just consider that, like multiply that by the denominator,
Uh-huh.
and that be the numerator, and just repeat the denominator. And what, like,
Just keep track of that negative. Just make sure if there's a negative that you take care of that. Uh-huh. Now, I didn't show the other way, but it works the other way.
like,
Okay?
I'm not worried
GFF
about
it?
this, but I'm just asking if that works.
Mm-hmm.
Okay.
Yep. Okay, so I'm not going to show the other way, but it should spit out x.
And we use like 3 minutes at least.
Do you want to try it?
Yeah, you don't want to.
Oh, okay. I'll give you 3 minutes. You said 3 minutes. I'll give you 3 minutes.
You got this.
I'll do it while you're doing that. But I forgot what it was, so. F was 2x over 3x minus 1, right?
It sounds like something like that.
G. It works.
Hey, yeah, that's just like I said.
That's just all the work, so we have it. It's on video if you want to go back and look at it. All right. We good?
Yeah.
All right.
It's just a lot of.
Now, the next, I think, natural question would be, if somebody gives you a function that's one-to-one, can you find its inverse? If someone gives you two functions, you can check to see if they are, right? But what if someone just gives you one function? Like, what if I would have started out and I would have just given you f of x is 2x over 3x minus 1. What if I would have started right there and I said, hey, find its inverse,
I'm sure.
right?
We haven't learned that.
Yeah, find inverse.
Function until you find the one that works.
There you go.
So that's what we want to do now. Now we know what the answer should be, right? The answer should be x over 3x minus 2, right? That's what the answer should be. But how would we find it, right? Well, this problem is actually really hard, so I don't want to start with this one. Let's start with the one right before it. What was the one before it? I gave you two functions.
X cubed minus 1.
Okay. And then the other part is what we're going to figure out, okay? So let's find the inverse of this one first, and we'll come back and do that harder one after. And I might even do another one before I do that one we just looked at. All right, so here's the idea. Think of it this way. We know that the original function, f, is going to take x, and it's going to spit out f of x, right? We want this new function to undo that, right? This new function, we want the new function to take f of x back to x, right? That function we want to be its inverse, right? So instead of me drawing three pictures here, just think of it this way. X goes through, f does something to it, the inverse function takes that answer back to x. So in some weird way, if you kind of look at this a little bit different, this x right here comes over here. We've always said that x goes in, y comes out, right? And that y needs to go back to what? X. So in some strange way, x and y switch places. Whatever x was in one function becomes y in the other. X in one becomes y. Yeah, look, let me give you an example. If I have a function f that does this, takes 1 to 5, okay? So this is x and this is y. Let's say this is what f is doing. You plug in 1, it spits out 5. What does the inverse function do with 5? It sends it back to 1, right? So you notice that over here, the x coordinate it actually corresponds to the y coordinate here, but here the y coordinate corresponds to the x coordinate here. So that's what I'm trying to get you to see. In f, the x coordinate becomes the y coordinate in the inverse function. And in f, the y coordinate becomes the x coordinate in the inverse function. That's going to kind of motivate why I'm about to do what I'm about to do. Because if I just show you how to do it, you'll be like, well, why do you do that? This is why, because of that switching. So to find the inverse, the first thing you do is you rewrite the equation and you replace f of x with y. So I'm going to write down what I did next to it. Or I'll write the steps out over here on the side. The first step, replace f of x with y. All right. So I've got the first step done. Second step, I'm going to just write it down. You tell me what I did. I switched the x and the y, right? I just, everywhere I saw a y, I put an x. Everywhere I saw an x, I put a y, right? Why would I do that? It's because of what I just showed you. With the inverse function, they need to switch places, don't they? So that's your second step. Replace x with y and y with x. And then the last, or second to last step, solve for y. So now you see the equation we have? Solve it for y. So how could I get this y by itself in this equation?
Well, you would need to
Add 1.
subtract it.
Yeah, you could subtract it, but because it's already positive here, why don't I just bring the negative 1 over? So add 1 to both sides. And then to get rid of a cube on a power cube on a variable, we take the cube root on both sides. Now, when you take the cube root, do you have to worry about plus or minus? The kids in the bridge going down? Do you?
Because if it's negative, it ain't gonna work.
Do you?
You only need to worry about if the root is even.
Only if the root is even. Remember? If it's square root, fourth root, sixth root, you have to do plus or minus. But if it's an odd root,
It stays the same.
it stays, so you don't have to worry about plus or minus. And that's a good thing. That's actually, we need that because if we had y is equal to plus or minus here, it would no longer be a function. Because you would have two inputs going to two different places, a positive and a negative answer. So that causes major issues when we have square roots or fourth roots. All right, and then now at this point, the last step is to replace y with the symbol f inverse of x. So you see this y right here? I'm going to write f inverse of x there. So it'll look like this. Cube root of x plus 1 equals the inverse function of f. And I can just write that backwards. That's what we had, right? I stepped out of the room. You verified that this was the inverse of this, right? But now what we did is we started with this and we actually generated the inverse ourselves. So on your test, you'll have two different types of problems. One problem will be, are these two functions inverses? And you have to check both ways. And then I'll have a different problem where it'll say, find the inverse of a function. You don't have to check, okay? You're trusting that you did all your work right. You're trusting that those two are inverses. But I'm not asking you to verify it for me. All right. Yes?
Where you say find the inverses, I mean, to check to see if these two are inverses, can we do that process to check?
No.
Pick one, and then see if
You could do that as a double check, but if you're asked to determine if two functions are inverses, you must do composition both ways to show it's true.
Because I guess it would kind of defeat the purpose of
Well, because that's the way you verify it. I mean, that's the principle it has to follow. It must do the composition. And you run into some danger. If you mess up something in here, you might get the wrong answer, you know. But if you verify it both ways, you should know yes or no whether it works.
basically the Savior Bridge do because he said so.
Yeah, this is almost one of those. This is almost one of those ones where I'm insisting you do it that way. And it's more because I can kind of kill a couple of birds with one stone with that. You have to demonstrate you know how to do composition, right?
Yeah.
You know how to do f of g of x.
Right.
I can ask you one question that takes care of that instead of doing a separate question saying, show me f of g of x.
I've noticed that you like to take one question and you just get multiple, you cover multiple things on one question.
I like that, yes. All right, before we do the other one, let's do another one that involves a fraction. 3 over 2 minus 5x. Find the inverse. This one still is not quite as hard as the one that we're going to do after this. So what's the first step? Replace f of x with y. Next step, swap x and y. Solve for y. Okay, in the last problem it was a little easier to solve for y because, it was, just move the 1 over and then cube root and we were done. Here y appears in the denominator, doesn't it? And we want y to be free and by itself, so we got to get it out of the denominator and up into the numerator at some point. So how can we get this y out of here?
Times it by y.
Multiply both sides of the equation by
2 minus 5y?
2 minus 5y, the whole expression. This will clear out the fractions. So I'm going to clear fractions at this point. So I'm going to multiply the entire left side by 2 minus 5y, the entire left side times that. And when I multiply the right side by that, what happens? Cancels out. You just get 3. Now I'm trying to get y by itself. I had to put this in parentheses. I'll show this step here. That's what I did, right? I have to have the 2 minus 5y in parentheses, and I'm trying to get y by itself. I can't free it unless I release it from the parentheses, but to do that I have to do what?
Divide by x.
I guess you could divide by x now.
So it'd be 3,
And if you divide by 2 minus by y, you should be doing what you previously did.
but you'd be left with the fraction.
What were you going
If
to
you
say?
left with a fraction again.
You can divide by x. No, it's okay to divide by x.
Oh,
It's just that's not the way that I would do it, so I'm like, eh. But
How would you
Okay, so what did you?
I would distribute the x to remove the parentheses.
Yeah, that seems like you're
But then you're going to get rid
got
of the
minus
x
5y
anyway, so you
x.
divide by x.
Let's do it both ways. I'll do it my way first, then I'll come back and divide by x later, okay? Okay, multiply the x through. You would get 2x minus 5 yx or xy, you can do it either way, equals 3. All you're trying to do is get y by itself, right?
So now divide by x.
Divide by x.
No, not yet. I'm going to move this to this side, or I can move this to this side and the 3 to the other side. I'm going to try and get the y term isolated. So do you want me to leave negative 5x over here, 5xy over here, and move the 2x over, or do you want me to move the negative 5xy to this side, make it positive, move the 3 over?
The negative 5xy just because that'll make it positive.
To make it positive, and then bring the 3 over?
Yeah.
Okay, so 2x minus 3 equals 5xy. Now divide by, we're trying to get y by itself. 5x. Divide everything by 5x. So when I divide this side by 5x, it's just y. When I divide this side by 5x, we get 2x minus 3 over 5x. That's it.
And the other way?
Now the other way, take that same, we were right here. Right there. Was divide by x, right? Okay, if I divide both sides by x, I get 2 minus 5y equals 3 divided by x, right? Then, you want to move the 2 over here? You want to move the negative 5y over there and move the 3 over x over here? Okay. Hey, I'm open to whatever here. As long as you don't break any rules, I'll do it. So this came over here, this one went over there, right? And then finally, divide by 5. So if I divide by 5, I have to divide 2 by 5, which gives me 2 fifths. Minus over here, if I divide by 5, I get 3 over 5x equals y. Agreed? Well, that's an answer. Do we have the same answers? We do. Because look, if I have a single denominator term, 2 in the numerator, I can split it into 2 fractions. I could put 2x over 5x minus 3 over 5x. And these x's cancel. We get 2 fifths minus 3 fifths, 3 over 5x. Same answer, written a little different. I'm not saying any is easy. They're both the right way. They're both the right answer.
Yeah, your way was quicker.
I'm a fan of being right. I don't care which way you get there. All right?
So when you,
So
like,
if we
on
ever
a
go on
test,
a road trip with this guy, let's not pick him.
well, I mean, we could go the direct route, or we could take the 5-hour detour.
Yeah.
We're going to Florida, you know, but let's go to New York first. Avoid all break.
That wasn't significantly longer, so I'm not too concerned about it. All right, let's take.
Well, we were the ones planning to go to New York. He was saying just go straight there.
Yeah, but we didn't know the route.
Well, we were just saying we know this will get us there.
Let's look at this one before I do the hard one.
Yeah, this guy we're just taking a plane. He knows where it's at.
Think about the graph of this. Is it a one-to-one function?
No.
It's not. Let's see what happens when we try and find an inverse without verifying first it was a one-to-one function. So let's go through the process of trying to find the inverse. We do y is this, right? We switch x and y. Hey, on the last problem, I forgot to write f inverse. We were supposed to write f inverse of x equals, I forgot.
It was 2x minus 3 all over 5x.
Something like that? Okay. But we kind of knew that. All right, switch them, now solve for y.
So add 4 to both.
Add 4 to both sides. And here's where you run into the problem. Square root, you have to do plus or minus because you're doing the square root, right? So that means y can actually take on 2 different values, and that violates it being a function. One-to-one function.
So we're done.
So, well, yes, but I want to see if maybe there's a way we can work around this. Here's the original graph. Right, there's the original graph, x squared minus 4. The reason why it didn't work is because it's failing the horizontal line test, right? Is there a way that I could restrict the domain so that it would pass the horizontal line test?
Like 0 to infinity.
There you go. So how about we cut off half of it, right? If I cut that half off the graph, would that pass the vertical and horizontal line test?
Yeah.
Yes? So what I can do back here is I can say, look, let's look at this function on the interval 0 to infinity. Or another way of saying this, x is greater than or equal to 0.
So we have to do that for this one.
If you're going to talk about an inverse, you must restrict it. All right? Now let's go through the same process. Here, right? Here, same. Here, same. What about this, though? Can we get a y value that's both positive and negative? No, we should only get what? Positives, because of our domain restriction.
So would you write, replace the equal sign with greater than equal?
No, I would just erase that and make only that the positive. All right? It's only gonna, there's only one thing that can happen here. I can only get a positive number. Because look, the only thing that's going to happen here, right? How can I explain this?
I get it.
You do?
If you would graph that, it looks just.
Yeah, look, because the x's and y's are switching places. So whatever x was here, right? That's the new y value. Then I switch those. This becomes the x, and this becomes the y. So if I come over here, this x is actually the y here. This can never be negative.
So when you would write it, would it be that, like f, the f inverse is greater or equal to x?
No? Sure?
How would you write the answer?
It's this. This is the inverse.
So you wouldn't write, yeah.
But what you'd have, see, I could not ask you to find the inverse of that function. I could ask you to find the inverse of that function. I have to restrict the domain in order for you to be able to find its inverse.
You could do a negative because you can't get rid of negative.
I could have cut it the other way. I could have instead,
Well, when you end up with imaginary.
nope, watch. If I do this and cut this side off and change this, then over here you would use the negative. That's what you would do.
Would that be a text, like on the test, would you write it out like that?
No,
Question.
what I want you to see here more than anything else is that not every function has an inverse because it fails horizontal line test. But we can get around that by proper restriction of the domain. And the most important place this is going to come up is in the next class you take, which is pre-calculus. In pre-calculus, you're going to be introduced to a function called the sine function. And there's also the cosine function, the tangent function. There's 6 trig functions. The sine function looks like this. You've probably seen sine waves before. And they go in both directions forever like that. And these are functions, aren't they? I mean, this is a function. Is it a one-to-one function?
No.
No, it is not. And so does that sine function have an inverse?
No,
Not like that, it doesn't.
it can't because it fails the.
It fails horizontal, right?
You can give it.
But we can. There is a function called the inverse sine function. And the way we do it to make it work is we take this highest point over here and this lowest point over here, and we take everything in between like that, and we cut the rest of the sine function off. So we restrict the domain, which is exactly what I just did here with this parabola. I restricted the domain half. That's the way we did it first, and then I could do the other half.
Kind of reminds me of the cube root function.
Cube root, what's this one?
The inverse sine.
A little bit, but it doesn't go forever. That's the only difference.
That's the only difference.
Yes?
So like on a test, if you gave us that function and asked us if it had an inverse, would we write no or would we write yes if you restrict the domain?
If I didn't give you this, you would tell me it doesn't.
Okay.
If I gave you this, then you would have to, do what I did there. Yeah. But again, the key to this is not because I really want to test you on it. It's more that you've been exposed to the idea